Radio rocks. A geologist looks under the hood. Prepared for the Cascades Amateur Radio Society by Dave Foster, W3IGT, April 20, 2021. Radio is the wireless transmission and reception of signals by means of electromagnetic waves. Rocks are solid pieces of the earth made of natural crystals. These sound like unlikely partners, radio and rocks, but from its earliest days, radio builders used the physical and electrical properties of rocks and the crystals that rocks are made of to solve design challenges. Yes, really. Rocks and the crystals they're composed of have been and still are being used in electronics. Each kind of crystal pictured here is an example. Different kinds of crystals come from different rocks. Granite used for countertops, real granite, not the fake stuff, always contains crystals of mica and quartz, and sometimes includes fool's gold too. Limestone is often the host rock for galena crystals. So what's the point? Simply this. Scientists first discovered the physical and electrical properties that make rock crystals useful in electrical circuits. Next, engineers and designers used the crystals in building electronic circuits. Later, scientific curiosity about why these natural materials work the way they do led to questions about how internal atomic structure relates to a crystal's behavior. Answers to these questions made further advancements possible and led to ATM machines, smart watches, GPS, barcode scanners, automobile computers, smart appliances, and modern transceivers. Let's focus in this talk on 3 examples of crystals from rocks that found their way into radios. Their names: galena, mica, and quartz. You will learn how these crystalline solids solved problems that stood in the way of radio development and what it is about them that makes them so useful. A bonus is the story of how one of these crystals played a vital role in winning World War II, and then, after the war, helped to build our modern world. When Ulysses Grant was president, no one dreamed of wireless communication. Still, in those days, every self-respecting physicist was experimenting with electricity. They tested anything they could get their hands on, including the rock crystals from the local geology museum. A German physicist named K.F. Braun discovered, to his surprise, that some weak conductors, such as galena, a lead ore, pyrite, known as fool's gold, and silly-sounding solomelane, a manganese ore, all disobey Ohm's law by permitting electricity to flow in a forward direction, but not in the reverse direction. Today, these crystals are known as semiconductors, and the electrical phenomenon is called the diode effect. 20 years later, there were people trying to send wireless messages in Morse code. They were easy to send, but not easy to receive, because the only detector was an invention called the coherer. When a strong radio frequency RF signal reached the coherer, metal filings inside would clump together or cohere to one another. When the filings clumped, their resistance dropped enough for a current to flow and ring a doorbell. The coherer had drawbacks. It needed a really strong signal to work, and it had to be shaken after each dot or dash to break up the clump so the next dot or dash could be detected. Nonetheless, it was the best Marconi had to demonstrate early radio communication. At this time, a professor in India named Jagadish Chandra Bose was experimenting with microwaves in the 12 to 60 gigahertz region. He invented waveguides and horn antennas, but was stymied when he tried to measure field strength. Coherers could only sense the presence or absence of radio waves, not their strength. His meters read only DC. It was Galena that came to the rescue. I presume it was after learning of Braun's discovery that some crystals exhibit the diode effect that Bose built and used the world's first UHF detector made out of galena. A half dozen more years passed before our friend Braun demonstrated a sensitive radio detector of his own design for long waves and intermediate waves. He used a fine wire called a cat's whisker on a crystal of that manganese ore, solamelane. With a crystal diode, even a weak radio signal could be detected, so it could be heard in a set of headphones. What a leap forward. Braun's crystal detector worked so well that overnight, galena crystals replaced the coherer, and the crystal radio was born. In fact, Marconi's Nobel Prize, awarded for the development of wireless telegraphy, was shared 50-50 with Braun. The radio shown on the left was manufactured by Marconi during World War I. It consists of coils, capacitors, resistors, and a galena crystal detector, the idea borrowed from Braun. No tubes, no batteries, nothing else. The radio on the right is a classic crystal set, like the one my dad built in junior high shop class in 1923. Galena crystals overcame the weakness of the coherer and gave us the first popular radio. You probably remember how crystal radios work. This part of the schematic looks familiar to any member of the American Radio Relay League. It shows an antenna connected to ground through a coil. A capacitor is connected across the coil to provide a tuning circuit. And hopefully this tuning circuit has a sufficiently narrow bandpass to tune out all but one station at a time. But that's not necessarily a given. The RF signal was detected by the crystal, so it could produce a sound in the headphones. Detection means demodulation. A modulated RF signal is illustrated at the top of this figure. Moving down, the RF signal is rectified by passing through a galena crystal. This produces a pulsating DC signal envelope that still contains RF pulses. The envelope represents an audio frequency signal. So next, a capacitor filters out the RF pulses. A list of abbreviations used on computer motherboards shows both the letter D and CR for diode. Where do you think the CR for diode came from? What's happening inside a galena crystal to produce the diode effect? This will take several slides, so stick with me. Let's start with the chemistry. Galena's chemical name is lead sulfide. To a chemist, a lead sulfide molecule is a single atom of gray lead metal paired with a single atom of yellow sulfur. A chemical molecule, of course, is the smallest possible particle of a compound that has the chemical properties of the compound. The paired lead and sulfur atoms are more properly called ions. However, in order to keep things more straightforward, in this talk, I'll use the word atom for both atoms and ions. Interestingly, to a geologist, there's no such thing as a molecule of galena. That is because galena is a crystal, and each kind of crystal has its own patterns of atoms arranged in three-dimensional space. Two atoms by themselves cannot establish a 3D pattern. Instead, geologists talk about a unit cell. A unit cell is the smallest bit of a crystal that has all the physical properties of the crystal. Crystals usually have flat, shiny faces. The geometry of the faces is directly related to the particular 3D arrangement of atoms inside the crystal. And galena crystals often have silvery gray square faces. Galena's unit cell is based on a cube. But wait, there's more. Galena's unit cell is more than a simple cube. It requires 14 lead atoms and 13 sulfur atoms. So let's start with this large illustration of a galena unit cube. Notice that there's a lead atom at each corner, and also a lead atom in the center of each face. There's a sulfur atom in the center of each edge. And a sulfur atom in the center of the cube. This produces a unit cell that is both face-centered and body-centered. Galena's unit cell is more than a simple cube. It requires 14 lead atoms and 13 sulfur atoms. If we look at the cube in the upper left-hand corner of this figure, we see that there's a lead atom in each corner and a lead atom in the center of the face. If we turn the cube and look at the side, we see, again, lead atoms in the corner and a lead atom in the center of the face. If we rotate the cube so that we're looking at the top, again, it's a lead atom in each corner and a lead atom in the center of the face. If we look at sulfurs, there is a sulfur atom in the center of each edge and a sulfur atom in the center of the cube. And that holds for the sides as well. Sulfur atom in the center of each face and a sulfur atom in the center of the cube. Sulfur, 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 sulfur. So if we count these all up, it turns out to be 14 lead atoms and 13 sulfur atoms. This produces a cube that is both face-centered and body-centered. The extended pattern created by the unit cubes connected one after the other is called the crystal's lattice. As you travel through a galena crystal's lattice, both the chemical composition and the crystal's physical properties remain the same. I've just said two different ideas that sound the same. However, there's an important difference between them. Generally speaking, every crystal has a chemical composition that is the same throughout its lattice. On the other hand, many kinds of crystals have physical properties that change depending on what direction you're holding the crystal. Later in this program, we'll consider crystals of quartz. In transparent quartz, light travels faster from the pointed end toward the bottom of the crystal than it does across the crystal from side to side. Same chemical composition, different speed for light. How do we begin to understand these things? Two kinds of evidence reveal the internal structure of crystals to scientists: crystal faces and X-rays. Not all galena crystals have square faces. The atomic-sized unit cells can also be stacked up into certain other shapes. Some stacks look like pyramids with triangular faces. Others take on more complicated geometric shapes, like this dodecahedron with 12 diamond-shaped faces. If you look very carefully at the crystal in this picture, you can see that the corners are cut off by a pyramid, like this example drawing over here. This group of galena crystal shapes can only come from a face-centered cube. In the year 1895, X-rays were discovered by Röntgen in Germany and Tesla in the US. 2 decades later, somebody figured out how to use X-rays to see patterns of atoms inside a crystal. These X-ray interference patterns were recorded on photographic film. Of course, it took decades before libraries of X-ray patterns were collected and enough measurements of layer spacings worked out for many different kinds of crystals. By the mid-1930s, enough was known that scientists at Bell Labs could begin thinking about building diodes from other crystals, such as the semi-metal germanium. With all this said, we can talk about what makes galena work as a radio detector. As natural crystals are created inside the Earth, they grow in a chemical soup, typically molten rock, as in a volcano, or in a mixture of superheated steam and dissolved crystals, like under a geyser in Yellowstone Park. Crystals grow as more atoms join onto the crystal face one at a time. This preserves the atomic arrangement of the unit cell as the lattice grows. The result? Nature creates crystals that are nearly perfect. Alas, there's always the chance that a few stray atoms will elbow their way into galena's extended lattice. Let's see what happens then. With all this said, we can talk about what makes galena work as a radio detector. As natural crystals are created inside the Earth, they grow in a chemical soup, typically molten rock, as in a volcano, or in a mixture of superheated steam and superheated water, like beneath a geyser in Yellowstone Park. As crystals grow, more atoms join on to unit cells one at a time. This preserves the atomic arrangement in the unit cells. The result? Nature creates crystals that are nearly perfect. Alas, there are always many different kinds of atoms in the soup, and there's always a chance that a few stray atoms will elbow their way into galena's extended lattice. In nature, several other metals are found, often alongside with the lead that is creating galena. Two of these metals are zinc and silver. Sometimes a loose atom of zinc will squeeze into a space between atoms, and the galena lattice will grow right around it, like a tree growing over a barbed wire fence. Other times, an atom of silver will show up where an atom of lead ought to be. Prospectors look for galena crystals with somewhat curved faces, like this one, suggesting that the lattice has been distorted, possibly by silver atoms. And that's significant for understanding how a galena crystal detector works. The growing galena crystal can get distorted at the atomic level by the occasional atoms that don't belong there. These foreign atoms can bring along extra electrons. This converts galena into an N-type semiconductor material with potential for one-way electron flow from the crystal into the cat's whisker. The crystal is the cathode, and the cat's whisker is the anode of this natural diode. As explained before, the diode rectifies RF, extracting or detecting the audio portion of the signal. Scientific attempts to understand the diode effect in natural crystals like galena contributed to the field of solid-state physics, with its theory of electrons and holes. Solid-state physicists and chip designers use band gap theory to explain how easy or difficult it is for electrons to jump across a crystal's face. Band gap involves electric fields, and they're measured in electron volts. If you know anything else about band gaps, you know more about them than I do. Except for one thing: low score wins. Band gaps are found in all true semiconductors. Galena has a smaller band gap value than, say, silicon or germanium. If galena had either a higher band gap or no band gap at all, it would never work as a detector in a primitive receiver like a crystal set. The fact that it does work opened the field of semiconductors to the human world. This flowchart for solid-state physics summarizes where we've been on tonight's whirlwind tour of the galena crystal. The right-hand side, LEDs and so on, we didn't go there, but we did go to the properties of elements like silicon and germanium and galena crystals. We talked about the crystal lattice in some detail. We mentioned the band theory of solids. We pointed out that galena is an N-type material, and when it is paired with a positive signal, as in a cat's whisker, you create a PN junction, which is, of course, a diode. And it was the understanding of diodes that led to the invention of the transistor. Our conclusion for this section is the atomic structure of crystal lattices explains why some crystals help radios to work. Imagine you're living 100 years ago. Today, radio is the latest fad, like the internet will be 100 years from now. To get into the radio game, you want to start up a manufacturing business. First, you need to decide what you can manufacture. So you borrow a book from Dick. From Dick's book, you decide to make and sell fixed capacitors. Next, you need to decide on what materials to use. So you talk to Steve after a ham radio club meeting. Steve points out that you will need a conducting material for plates, an insulator to go between the plates, a couple of leads to attach your capacitor to a circuit, and a case to enclose the whole thing. You check out various metals that come as thin foils. Mike suggests tin foil for a standard capacitor because it solders easily, and silver for top of the line units, since silver is the best conductor. For leads, you settle on tinned copper wire. You run into Jeremy at the general store, where they sell radios on the side, and he says his buddy Mark works for a company that makes a new material called plastic. It's molded under pressure. You figure the pressure will squeeze the capacitor plates closer together during the final step in manufacturing. You settle on Bakelite plastic. You want to build the world's best fixed capacitor, so you place a long-distance telephone call to Wes in Chelsea. You ask him about insulating materials. He reminds you that the closer you can get the plates to each other, the more capacitance you'll get for the buck. He says, better focus on insulators. You go to the Carnegie Library and look up insulators. Here's what you find. Breakdown voltage is just what it sounds like. It's measured in kilovolts per millimeter of thickness. A millimeter is about half the thickness of a pencil lead. How high does voltage have to be before it breaks through? The higher the value, the better the insulator. Dielectric constant compares how big a capacitor value you get with a given insulating material versus replacing that material with a vacuum. The best is 1.0, a pure vacuum, since in a vacuum, there's nothing to conduct electricity. The closer you can get to 1.0, the better. You learn that mica's dielectric constant is pretty low. Dave is taking a class in geology at Jackson College. He tells you that mica peels off in thin layers. High breakdown voltage, low dielectric constant, peels into thin layers. You decide to go with mica. 10 years go by. You're selling lots of capacitors and making lots of money. You have time to wonder what it is about mica that makes it such a great insulator. So you hire a consulting scientist to tell you. His report includes the following. 20 years ago, there was a discovery. X-ray images of crystals produce regular patterns of dots on photographic film. These patterns reveal the arrangement of the atoms inside the crystals. Mica has recently been X-rayed, and the pattern of atoms is now measured and understood. Well, mostly understood. Chemical analysis reveals that the chemical elements in mica are silicon, aluminum, potassium, and oxygen. Silicon and aluminum are chemically attached directly to oxygen, while the potassium doesn't seem connected to much of anything. The report goes on. There's something unusual about the way the oxygen joins up with the silicon and aluminum, and we don't understand it yet. Chemical analysis shows a ratio of 1 silicon atom to every 2 oxygen atoms. But X-rays say it's 1 to 4. Further research will be required to figure out this apparent contradiction. Let's fast forward to the year 1999 and pick up on the SiO2 controversy. Silicon has 4 electrons available in its outer shell. Oxygen wants two more. Common sense says that the silicon will loan two electrons to each of two oxygens. But X-rays say that silicon loans out one electron to each of four oxygen atoms. So who is correct? If each oxygen atom borrows only one electron from each silicon, then it has to find one more electron. It might borrow the second electron from a different silicon atom. Now each oxygen would be joined at the hip with two silicon atoms, and each silicon atom connected to four oxygen atoms. This is now accepted as what actually happens. We call these silicon-oxygen groups silica tetrahedrons, and they link together corner to corner. As they join together, each silicon atom becomes linked to four oxygen atoms. One silicon, four oxygen. And each oxygen atom becomes linked to two different silicon atoms. So each silicon atom becomes tied to four additional silicon atoms by way of its linking oxygen atoms. The result is a very strong three-dimensional network. The crystal structure of mica is not a simple cube like galena. It is a complex combination of silicon, aluminum, and oxygen tetrahedrons, plus a few potassium atoms. As this crystal is rolled around, you can see some sort of ring structure at the top. These are strong interlocking hexagons of silicon oxygen and aluminum oxygen tetrahedrons. If the crystal is turned on its side, however, we suddenly see that the network is actually made of two flat layers, like slices of bread in a sandwich. The layers are separated by purple potassium atoms, like the filling in a sandwich. The potassium doesn't seem to be connected to anything else, and actually, it isn't. It's held in place by the so-called weak force, which is only about 1/1000th as strong as the silicon oxygen layers. You can separate sheets of mica with your fingernail because of potassium's weak bonds, but because of the strong silicon oxygen bonds, you can't break a 1/8 inch thick layer of mica, even using both hands. This fact dramatically illustrates how a crystal can have different properties in different directions. Crystal structure explains it all. Mica capacitors are still in use in 2021. Maybe you saw the article in QST from February of this year, titled, "Using Your 160-meter vertical on 80 meters." The article contains this quote: "If running legal limit power, the current on 160 meters is high due to low antenna impedance, about 5 to 6 amps RMS. On 80 meters, the voltage is high due to high impedance, about 1700 volts RMS. So the components must be able to handle these current and voltage extremes. My unit uses a fixed 300 picofarad surplus silver mica transmitting capacitor from a friend's junk box. Or you can use a variable capacitor if you can find one." Close quote. Geologists know that natural resources such as mica are not in endless supply. Because the easy-to-find deposits of mica have already been exploited, supply has dwindled and the price skyrocketed. For example, a 1 microfarad 1500 volt mica will cost you well over $200. However, there are still plenty of small mica crystals out there and plenty of small mica capacitors too. Today's high voltage surface mounts use mica. Just turn to a Mouser or DigiKey online catalog to find miniatures rated at 100 or 500 volts and priced under $2. Conclusion: don't let anybody tell you they can't find a rock in any of today's radios. Now, let's move on to World War II. The year is 1940. The Battle of Britain is taking place in the skies over London. Here in the US, another kind of battle is shaping up. The Army Signal Corps is battling over which type of tuning circuit to specify for military transmitters and receivers. The way it's always been done is to build oscillators from coils, capacitors, and resistors using tight tolerances to minimize frequency drift. The top brass are lining up with the way it's always been done. The other side argues for the wave of the future, crystal-controlled oscillators with thin vibrating wafers of quartz that lock onto a frequency and won't let go. Young Signal Corps officers and civilian experts favor crystal control. This book tells the dramatic story of how rock crystals will help win World War II. It tells the pros and cons of traditional oscillators versus crystal control. The traditional oscillator offers continuous tuning across each band, while crystal control requires separate crystals for each frequency channel. With a traditional oscillator, if the enemy jams a particular frequency, radio operators simply rotate the dial to an alternative frequency, while crystal control's narrower tuning makes it possible to cut through a lot of interference. With a traditional oscillator, variations in temperature or humidity cause frequencies to drift, requiring constant retuning. Vibrations in a tank rolling down the road jiggle a radio off frequency. And when multiple radios operate in a network, somebody's bound to be slightly off tune. With crystal control, tuning involves throwing a switch to go from one channel to another. A skilled radio operator isn't needed next to every fighter pilot or tank commander. Crystal control provides an extremely sharp resonance spike, which means narrow bandwidth tuning. The benefit? Interfering stations close to your frequency are scarcely heard. In a tuning circuit, Q measures how narrow the bandwidth is. This graph compares the resonance curve for a Q equals 5 with Q equals 20. For comparison, the Q of a quartz crystal oscillator is typically greater than 100,000, and Qs of 1,000,000 or more are not unheard of. In January 1941, field tests are conducted at Fort Knox, Kentucky, and the results are dramatic. Cleaner signals, less background noise, crosstalk disappears. Field commanders from all branches are immediately convinced that fighters in the field need the improved signal clarity that goes with crystal control. What ham radio operators knew all along is right. Crystal control is the way to go. There's only one problem: where to get enough crystals. At this time, only a handful of small manufacturers are grinding crystals to frequency. Most of these companies have been founded by hands. Their total output is a steady 100,000 crystals per year. Their best customers are telephone companies and other hands. Yet the Army needs crystals by the millions. Faced with this challenge, the Signal Corps created a winning strategy: expedite all paperwork for crystal manufacturers. Put together a small, top-notch technical team of problem solvers. Work closely with the manufacturers. Reward the winners. Support those having troubles. Communicate with everybody through frequent newsletters. Share problems and fixes among competing manufacturers. The largest crystal company in 1941 is Bliley Electric. Dawson Bliley, W3IGT, started the business 10 years ago in his mother's basement. He was grinding and selling crystals to other hands. Now, in 1941, he employs 70 people. By 1944, he will employ 1,500 people and be running 2 factories 24 hours a day. In Los Angeles, Herb Blazier, W6DCE, founded Monitor Piezo about the same time as Bliley. As World War II approaches, he is sitting down to write a business plan. First, he is designing a process that uses the crappiest grade of quartz crystals, the stuff nobody else wants. That way, he figures, he can always find plenty of raw material, even when supplies become tight. Next, he's moving his factory to an upscale neighborhood in Pasadena and undertaking to build up a workforce made mostly of local young women with a sense of commitment. High school grads, preferably with a father or brother in the armed forces. To this, he's adding good wages, good working conditions, and free coffee. He's topping this off with a plan to keep the foreman off the production floor, out of the workers' hair. Then he'll let his employees get down to work. This plan would become a huge success, with inspectors finding only 1 reject per 250 crystals, an incredible 99.6% acceptance rate. The Army technical team was headed by a physics professor. 4 geologists and 1 engineer rounded out the team. As problems arise, they are tackled jointly by the technical team and the crystal manufacturers themselves. In a nutshell, going from a raw quartz crystal to a radio crystal involves cutting a wafer out of the raw quartz crystal at the proper angle, grinding it to frequency, and mounting it in a case. The tricky part is orienting the crystal to a precise angle before you start cutting. Geologist Clifford Frondell on the Army's technical team worked out the technical details so quartz crystals could be oriented to the proper angle right on the assembly line. This one innovation reduced waste by up to 40%. Production grew. It grew and grew from 100,000 crystals per year in 1941 to an incredible 28.5 million crystals per year in 1944. The payoff? Quartz crystals are reducing bandwidths, so many more conversations can be packed into each segment of spectrum. Now every tank operator can talk to every other tank operator, and every fighter pilot to his wing leader. Infantry units have communication with the push of a button, giving rise to the newfangled walkie-talkie. Later in the war, crystals will make FM radio possible. Enemy field units were not equipped to receive FM signals at all. The enemy's radios used traditional oscillators. Their signals occupied more bandwidth, and their receivers received more static. Less ability to talk reduced their ability to maneuver. The Battle of the Bulge is a case in point. It was a brilliant German battle plan that came close to succeeding, but for our added advantage in mobility provided by crystal-controlled radios. In 1943, an item in Life magazine reported, in proportion to size, those little glass-like quartz wafers are perhaps the most remarkable tools that science has given to war. When the story of the almost incredible progress in research and manufacture of radio crystals can be told, it will prove to be a tale of one of this war's greatest achievements. No less significant will be the fruit of these advances to a new world at peace, where crystals will be the vibrating hearts of most telecommunications equipment. Why have these little glass-like quartz wafers become the vibrating hearts of virtually all modern electronics? Quartz crystals are good insulators. That means they're not interfered with by electrical fields. They are mechanically solid. The interlocking silica tetrahedron make that work. They are temperature stable. They are moisture resistant. They are highly precise. And they are piezoelectric. Piezo comes from the Greek word for squeeze. Put a quartz crystal in a vise. As you tighten it, electric current flows. Think about it. Squeeze a rock and electricity comes out? Incredible. As if that's not enough, when you apply an electric current to quartz, the crystal morphs its shape. The response time is exceedingly fast, virtually instantaneous. The shape change takes place in well under a millionth of a second. With this talk, we have a YouTube video that explains how all this works. The guy in the video is Steve Mould. He's both entertaining, and he uses peanut butter jar lids and a barbecue lighter. But he's also scientifically correct, and he does go fast. So before we watch him, here are a couple of basics. We discussed the SiO2 versus SiO4 controversy when talking about mica. Since quartz is nothing but silicon and oxygen, the story is exactly the same here. Each silicon atom is surrounded by 4 oxygen atoms, creating a 3-sided pyramid or tetrahedron shape. Each of its 4 oxygens connects to another silicon, building a strong 3D network. Quartz crystals want to be hexagonal, but it's a bit of a struggle. Quartz crystals are 6-sided and have 60-degree angles, yet the unit cell is not a real hexagon. It's a tilted rectangular shape called a rhombohedron. Anyhow, when 3 rhombohedron unit cells are fitted together, out comes a hexagon. When you look down a quartz crystal from its pointy end, you see the edge of 6 faces, but those faces don't have equal widths. I guess that's caused by the way the unit cells fit together. Anyway, the result are crystals that are not perfectly symmetrical. In summary, rocks and their crystals have played significant roles since radio's earliest beginnings. Their usefulness in radio results from the kind and arrangement of atoms within the crystal. The crystal lattice is made up of unit cells, not molecules. Understanding the geology and physics of unit cells is what made possible today's solid-state electronics. As for World War II, President and Commander-in-Chief Franklin D. Roosevelt said, "We have faith that future generations will know that here, in the middle of the 20th century, there came a time when men and women of goodwill found a way to unite and produce and fight to destroy the forces of ignorance and intolerance and slavery and war." Radio's rocks played a major part in that success.